Let's talk about the Z-transform. Why do we need the Z-transform? To answer the above question, we should analyze the discrete time Fourier transform of the following sequence, where the absolute value of alpha is greater than 1. Here's the analysis shown here. Note that the discrete time signal x of n is an infinite geometric series. Thus, we can try to obtain the sum of the sequence using the geometric expression, given that the absolute value of r is less than 1. But the ratio of x of n, or alpha, or the absolute value of alpha, is greater than 1, so the sum diverges. So we cannot use the geometric series expression. In conclusion, we need the Z-transform to be able to convert any discrete time signal x of n to its frequency domain representation. The Z-transform allows us to determine if the DTFT exists for a given signal. It allows us to determine the stability of infinite impulse response filters. We will touch on this later. And it's another tool to analyze LTI systems. Now that we know why we need the Z-transform, let's try to define it. Any discrete time signal x of n has a Z-transform representation given by x of z is equal to the sum over all k from negative infinity to infinity of x of k times z to the negative k, where z can take any value from the complex plane. Let's talk about the relationship between the Z-transform and the DTFT. Note if we substitute z equal to e to the j omega into the expression for the Z-transform, we obtain the expression for the DTFT. Since the DTFT is periodic, we choose omega to be between negative pi and pi, so we can think of z equal e to the j omega as the unit circle. The values of z that lie within but not on the unit circle form the region of convergence for infinite length discrete time signals. The region of convergence is where the expression for the Z-transform converges. In other words, it is the region where the infinite length discrete time signal x of n has a defined DTFT. For any finite length discrete time signal x of n, the region of convergence is the entire Z-plane except for the origin. We will now turn to Dr. Wong to show us some examples.
So example number 1. If my signal x of n is of finite length. So suppose my signal x of n has value, say, b sub n for n ranges from 0, 1, all the way up to, say, big L minus 1. So the length of the signal is L. Its value is 0 for all the other n. Okay, so that's one way to write it. If you want to plot the signal will look something like this. At time 0, its value is b sub 0. At time 1, its value is b sub 1. So on and so forth, and all the way up to the time n equal to L minus 1. Its value is b sub L minus 1. And beyond this range, or outside this range, the signal value is 0. So it has a length of L, and it's the finite length signal that we are looking at here. So we want to actually calculate the Z-transform of this simple signal. And according to the definition that we have on the side of the other board, on the other side of the board, we know that the Z-transform of this signal is basically, let me write down the definition and then we will simplify this. So basically this infinite degree polynomial. And we can actually do the substitution, and actually we can simplify the polynomial immediately because we know that the signal value at time 0 is b0, time 1 is b sub 1, so on and so forth. And beyond this range or outside this range, the signal value is 0, which means that when I actually calculate the polynomials, most of the coefficients of the polynomial is going to be 0, except the coefficient correspond to the power 0, n equal to 0, the coefficient correspond to the power n equal to 1, with, power negative 1, so on and so forth, right? So which means that I can actually simplify this. I can start the polynomial from n equal to 0 all the way up to n equal to L minus 1, and that's it. And of course, I can substitute the value in here, and the value for the nth coefficient is just b sub n. Okay. So what I end up, well, this is one way to write it. The other way to write it is your usual way of writing down a polynomial. So the first coefficient is b0, and the power or corresponding to this polynomial for this coefficient is 0. So z raised to the power 0 is 1. So we should just write it as a constant. And then b sub 1 is the coefficient for the term c raised to the power negative 1, plus b sub 2 is the coefficient corresponding to the terms of c to the negative 2, so on and so forth. The last coefficient is b sub L minus 1, and the term associated with it is z raised to the power L minus 1, negative L minus 1. Okay, so what we actually end up getting is a finite degree polynomial. And the degree of the polynomial is actually what? L minus 1. Okay, so the C-transform is just this simple polynomial for the case of a finite name signal. Okay, so the question I ask you is, what is the region of convergence for this particular C-transform? But first of all, let's look at what is the definition of region of convergence. The set of the complex number when I do the substitution into this z here in the polynomial, I can calculate the value. I can evaluate the polynomial, right? It will be 0 everywhere else. Everywhere else but 0, right? Is that what you're talking about? Okay. If you look at the complex plane, that like what we draw before. So again, horizontal axis is the real part. Vertical axis is the imaginary part. Basically, any point on the complex plane, we can substitute into the z here. Since it is finite degree polynomial, we can always evaluate the polynomial, right? But the trick here is to look at the case where, because this is actually a polynomial in c to the negative 1. So which means that there is actually one exception. Exactly, that exception is the origin. Right? The point at the origin, c equal to 0, that point when I do the substitution, I run into a problem because, say for example, this term, 0 raised to the power negative 1 is 1 over 0, which is not defined. And only in this case we run into a problem. So the region of convergence, let me write down here. So the region of convergence associated with this C-transform is everything but the origin. And let me use this notation. So I'm going to write down as C such that its absolute value is bigger than 1. Okay, so that's the way to write it down. So, because for the origin, the absolute value of z or the magnitude of z is equal to 0. So anything but that will be the region of convergence for this C-transform. Okay, so that's the simple case. That means what? Let me draw the picture again. So if this is the region of convergence for that C-transform, and the unit circle is here, right? So the region of convergence will contain the whole unit circle. That means I can do the substitution where z is equal to e to the j omega hat. Right? So if I do the substitution, I would get back the DTFT. So the DTFT of this signal does exist, and it can be calculated like this. Okay, so let's look at another example. So example number 2. This is an example of our previous signal. Alpha raised to the power n times the unit step signal. Okay, so we try to calculate the Z-transform for this guy. We actually did the step. We all pretty much did the step for the case where the absolute value of alpha is strictly smaller than 1. So we just try to do the other cases here. But we'll do the general thing. And if you recall, the Z-transform is defined to be this infinite degree polynomial whose coefficients are the value of the signal at time n. So we just need to do the substitution, just like exactly the step that we went through before. We end up getting this. And once again, because of the fact that this is the u of n is the unit step signal, so when I consider all the terms in the polynomials, I can actually basically throw away all the terms for which n here, the index, is strictly is actually negative, right? Because we know that for those negative n, the value of this unit step signal is going to be 0. And for those positive, for the positive n's, the value of the u of n is actually 1. So we just need to calculate this sum, basically. And once again, we're going to use the same tool that we used before, the infinite geometric series formula. We put these two things together. Okay, so this is my A. So we have basically two cases. The first case is when the absolute value of alpha times c to the negative 1 is strictly smaller than 1, which is the case that we can use the formula. And in this case, we know that the value is 1 over, the sum here is 1 over 1 minus alpha times c to the negative 1. That's our Z-transform value. And on the other hand, for the other cases, well, basically means that the absolute value is bigger than or equal to 1. Let me write down here. The big absolute value here is bigger than or equal to 1, then this thing doesn't exist or diverges. Okay, so we basically, once again, work out the region of convergence for the Z-transform of this exponential signal. Okay, it could be exponentially decaying or exponentially increasing. And so what is the region of convergence in this case? The region of convergence are those complex numbers. If you try z, such that you take the inverse of it or the reciprocal of it and times alpha, and you take the absolute value, and that absolute value is strictly less than 1, right? That is the case that you can calculate the sum. Okay, but you can also simplify this a little bit. In particular, you can write this as this guy here, as this. Right, so what I'm saying is alpha times c to the negative 1, if you take the absolute value, is equal to the absolute value of alpha over the absolute value of z. Agree? So if you have this strictly smaller than 1, and you can now move to the other side, which basically means that this region can be expressed algebraically or equivalently as the absolute value of c bigger than the absolute value of alpha. Right? Agree? So if you have written it in this form, the region of convergence into this form here, you should be able to plot it on the complex plane. So if you are, maybe I'll plot it on the other side of the board. So if you have to plot the region of convergence, which is specified by the expression here, or by this particular algebraic expression here, on the complex plane, what kind of plot do you expect to see? Anybody know? This is the region of convergence which is expressed as the absolute value of the complex number to be bigger than the absolute, must be strictly bigger than the absolute value of alpha. Alpha is some constant. Anybody know what kind of region is that? Okay, let me ask you. So what is this? What is this curve? This is a curve, okay? What is this curve? This is a curve of a... No, on the complex plane, it's not a straight line. okay, let me see. Let's simplify this further. So what is this curve? This is a complex number, right? It's not a horizontal line. It's a circle with radius 1, right? Okay, so what is this? What is this curve? A circle with radius absolute value of alpha. Okay, so this is a circle, the curve of a circle with radius equal to absolute value of alpha. So what is this now? It's outside that circle. Okay, so every point that is outside that circle. Okay, so this is the region of convergence for this particular signal. So as you can see, it depends on the absolute value of alpha. If the absolute value of alpha is strictly smaller than 1, then what do we have? That means the circle here will have a radius that is smaller than 1. That means the unit circle, if I plot the unit circle in this particular situation, the unit circle will be here. Right, so the region of convergence in this case will contain the unit circle. The unit circle is completely inside the region of convergence, and hence, once again, we can do the substitution of z equal to e to the power j, negative j omega hat. That will reduce to dTFT. And if you substitute z equal to e to the j negative e to the negative j omega hat into z here, you'll get the expression that we had before, which is the dTFT of this signal. Okay. On the other hand, if you have the other case where the absolute value of alpha is bigger than or equal to 1, then you have a different situation. In this particular second case here, the region of convergence will be this, and this radius is going to be bigger than 1 or equal to 1. That means the region of the unit circle is going to be inside here. So as a result, the region of convergence will not contain the unit circle, and hence you cannot do the substitution of c equal to e to the negative e to the power negative j omega hat. Remember, the region of convergence is anything that is strictly outside this circle. So if alpha is exactly equal to 1, then this circle, the unit circle will be just basically this broken line here, a broken curve here, and yeah, it's still outside of the region of convergence. So the region of convergence still doesn't contain the unit circle in that case. So this is a nicer thing, because if we do have a signal where the absolute value of alpha is actually bigger than 1, so for example, if you have the unit step or the exponentially increasing signal, we cannot deal with the dTFT, but we can still deal with the Z-transform, because at least for those Z that are outside of this circle, which means that inside the units, the region of convergence, we can still calculate the sum and still be able to deal with it. Okay, so that's where the generalization comes from.
In conclusion, for any finite length signal, the Z-transform of the signal could be written as a polynomial with L terms. For any infinite length signal, the Z-transform is obtained if the region of convergence of the signal is within the unit circle. Otherwise, it does not exist. Talk about the system function, or transfer function. Recall that if you have an LTI system with an impulse input, the output will be the impulse response, h of n. The transform of h of z, given by this expression here, is called the transfer function. If we substitute z for e to the j omega, we obtain the frequency response of the LTI system. Here's an example of the transfer function. Consider the following FIR filter. From the expression for the z-transform, we find that h of z in the following polynomial form. Here's another example of the transfer function. Consider the following infinite impulse response filter. Using the geometric series expression, where the absolute value of r is less than 1, we get the expression for the z-transform, where the absolute value of r is equal to 1/2, which is less than 1. So it lies within the region of convergence. Now that we've talked about the z-transform and seen some examples, let's talk about some of the properties. Linearity, time delay, and convolution are all properties of the z-transform. Their expressions can be found here on this slide. Note that the convolution property translates to multiplication in the frequency domain. The z-transform also follows the properties of cascaded LTI systems, where the overall impulse response is found by convolving the individual impulse responses, and the overall transfer function is the product of the individual transfer functions. Let's look at some examples using the z-transform properties. Here is an impulse response expression. Using the infinite sum formula and one of the properties, we obtain this expression for the transfer function. Which property did we use? Here's a slightly more complicated problem. Here is the expression for the impulse response, and here is the resulting transfer function. How many properties did we use? In conclusion, z-domain analysis is another tool to analyze LTI systems. Here are the steps for z-domain analysis. Obtain the transfer function from the impulse response. Calculate the z-domain input from the time domain input. Then use this expression to calculate the z-domain output. Use the inverse z-transform to obtain the time domain output from the transfer function. We will talk more about this later. We will now have Dr. Wong give us some examples of z-domain analysis.
So the first signal, let's call this x of n, which is a signal of length m. Is that m that I use? Yeah, say suppose the first signal is a signal of length m. So its value is a sub n for time n range just from 0 all the way up to m minus 1. And 0 for all the other n. So this is a finite length signal of length m. And suppose I have another signal, say h of n. You can treat this as an impulse response if you want to. And it is also another finite length signal. It has the value b sub n, where n ranges from 0 all the way up to L. Is that what I do? Let's see, L minus 1. So it has a length of L. In this case, 0 otherwise. Okay, so of course, I mean, if I treat this as an impulse response, so we have an FIR filter here, and this is the input signal. The output signal is going to be a convolution between these two guys. So I convolve these two signals to get the output, or get the convolution signal y of n. And we all know how to do convolution, I hope. Then we are going to actually go through the steps of the C-domain analysis one more time. And we know that according to what I just said before, the output C-transform, or the C-transform, the convoluted signal, is the product of these two guys, of the C-transform of the impulse response, h of z, or the transfer function, and the C-transform of this input signal, x of n. Okay, so let's look at this case, and we'll just work this out, see what happens. And according to our previous example, we know what are the Z-transform of the impulse response. We also know what is the Z-transform of the input signal x of z. Right? So what are they? We worked them out before. This is a finite length signal. This is also a finite length signal. And in this particular case, we already worked it out, right? Because that's an FIR filter. The transfer function of an FIR filter is given by this, right? It is a polynomial of degree L minus 1, actually. So it is a polynomial like this. So it's B0 plus B sub 1 C raised to the power negative 1 plus B sub 2 C raised to the power negative 2 plus B sub L minus 1 C raised to the power negative L minus 1. Right? So it is this polynomial. Second guy, the Z-transform of the input signal, where input signal is that finite length M signal. It's the same thing, right? So the Z-transform is another polynomial, and the coefficients are those ANs, and the degree of that polynomial is M minus 1 instead of L minus 1. So it's A0 plus, A sub 1 of C to the negative 1 plus A sub 2 C to the negative 2 plus all the way up to A M minus 1 C raised to the power M minus 1. Right? Agree? So we know now, according to our convolution property, we know that the Z-transform of the output signal is the product of this guy and this guy. So what is this Z-transform? What kind of Z-transform it is? It's a product. This is a polynomial, and this is another polynomial. If you multiply two polynomials together, what do you see? What do you get? Another polynomial, right? So what is the degree of this polynomial? You have a polynomial of degree L minus 1. You have another polynomial of degree M minus 1. You multiply these two things together. What is the degree of the product polynomial? L plus M minus 2 is the sum of the two degrees, right? So of course, I don't want to multiply by L, but I know it is a polynomial of degree what? L plus M minus 2. So I can actually just write like this. Let's assume let's write the coefficient of that polynomial to be C0, C sub 1, C sub 2, all the way up to C sub what? What's the last one? L plus M minus 2, right? C raised to the power L plus M minus 2. Right? So assume you did the multiplication of the polynomial, and then you get all the you basically group all the terms with the same powers together, and then calculate the corresponding coefficients associated with each of the term, and those are our C's. Okay. But we also know one thing. According to our time domain analysis, my output signal can be obtained as the convolution between h of n and x of n, right? And this guy here, this long polynomial, is the Z-transform of the output signal of y of n. And so that means, let me write down here. If I do this time domain analysis first, do the convolution, and then find the output signal. So I find the value of y, all these y's of y of n here. Then if I want to actually find the corresponding Z-transform of that y of n, I would actually calculate this sum, right? Agree? So if I know all these values, I did the time domain analysis, and I know all these values, and I just use them as coefficient of this infinite degree polynomial, and then throw it in there, and I get the Z-transform. But on the other hand, using convolution property that we had before, we know that this guy is a polynomial with coefficients Z0, Z1, Z2, and all that stuff. Okay. This is a polynomial, this is a polynomial, so you have two polynomials. I tell you that they are actually the same. What does that mean? That means I can equate the coefficients, right? And what's the result? I know that I basically can write like this. I can write like y. This is my y sub 0, and this is my y sub 1, so on and so forth. And the last one is my y sub L plus m minus 2, like this. Right? And for all the other value of y of n, they must be 0. These two polynomials have to equate, which means that the coefficient must be the same. So we have this. So this z0 is actually my y of 0. This c sub 1 is actually my y of 1. So that's actually give us one method to do the inverse, the last step of the C domain analysis. If we can find this, we can write our output write our Z-transform in terms of a polynomial. Then I just basically read off the coefficient. This coefficient is my y0. This coefficient is my y sub 1, and this coefficient is my y sub 2, so on and so forth. So that's one way to do the inverse Z-transform. And actually, this example tells us one more thing. We can obtain all these y0, y1, y, all these output signal by doing convolution. We can also, from what I just said, doing the C domain analysis, and obtain all these coefficients by basically multiplying these two polynomials, right? That means what? Convolution is nothing but polynomial multiplication. That's it. So remember we have two different ways of actually doing convolution. One way is to use the pictorial way of doing convolution. The other way is to use the table in the book. And of course, that's nothing but just bookkeeping, different bookkeeping method to calculate the sum. And now we have a third way. The third way is to do polynomial multiplication. So suppose I have a signal. These are the signal values. So one thing you can do is to form this polynomial. I have another signal. Again, these are the values of the signal at different time. And you form this another polynomial. And if you want to do convolution, you just multiply these two polynomials, find out all the coefficients and the corresponding coefficients of the overall polynomial, of the product polynomial, is going to be your convolution result. So that's another way to do convolution. So I guess everybody knows how to do polynomial multiplication, right? It's a very tedious process, but the algebra is actually very simple. At least the steps are very simple. So that's another way to do multiplication. Convolution. So convolution is nothing but polynomial multiplication, turns out.